Hi, this is part one of an example of graphing a function that's given to you in factored form. And we are going to take a look at this function here, 2 times x minus 8 times x plus 3 times x minus 4 times x plus 7. And your quest is to graph it. The first thing I notice is that the degree of this is 4, because if I were to multiply all these parentheses together, I get x to the 4th. Now the other way to look at that is if it's in factored form, you just add the exponents on each of the parentheses of the factors, and there's 4 ones, so it's 1 plus 1 plus 1 plus 1 is 4. This is degree 4. That tells me that the end behavior is going to be in a certain way. That tells me that the end behavior is going to behave like the ends. It's a positive 2, so the end behavior is like the ends of x squared. Goes up to the left, goes up to the right. Positive, even degree. The first step is to look at all the zeros and mark them on the x-axis. So I go to 8, 1, 2, 3, 4, 5, 6, 7, 8, and I just put a little x there. Just a little mark. I know that's a point in the graph because x equals 8 makes the graph 0. Then I go to negative 3, 1, 2, 3, and I make a mark on the graph. I know y is 0 there. I go to 4, 1, 2, 3, 4, and I mark the graph. I go to negative 7, that was 3, 4, 5, 6, 7, and I mark the graph. So I graph the zeros, and then I look at my end behavior. To the left of the leftmost 0, my function goes up. So I just kind of sketch an arrow that goes up. At the right end, after the rightmost 0, my function also goes up. Now notice I'm not being really accurate. I don't know that at x is 10, my function is actually equal to 2, though I could choose to plot those points. I can plot one point easily, and that's the y-intercept. When x is 0, I get 2 times negative 8, which is negative 16, times 3, which is negative 48, times a negative 4, which is 196, times 7. You get the idea. I would have a point way up here, I believe. I'm not going to worry about that for now. I'm looking for the shape. I want to know what goes on between each of these points where the function is 0. In calculus, whether your graph is above or below the axis in each of these intervals is what becomes important. So, the degree is 4. None of my roots are repeated. None of my zeros are repeated. That means each has what we call a multiplicity of 1, and at each 0, we cross through the axis. We don't just touch and turn around, we cross through. So I know I cross through the axis here, and I know I have to come back to cross through here. And I know I have to come back and cross through here. And I know I have to come back and cross through here. I've paid no attention at all to the y-scale. That's fine. Here's your general shape. If I really wanted to, I could have plotted some points. I'm not going to make you do that. I want general shapes. So this is a sketch or an estimate of the shape of the graph of this. The only thing the 2 affects is how high the y's would be, by the way. If I put a 5 in front of there, your shape could be exactly the same. So let's recap the process. You identify the degree and whether the term in front is positive or negative. This one is a degree 4 with a positive leading coefficient. Degree 4 is even, so it behaves like x squared. This is positive, so it behaves like the ends behave like positive x squared. I plot each of the zeros, and every x that makes a factor 0 gets marked on the x-axis. Then I look at my end behavior, and at the leftmost 0, I follow the end behavior to the left. In this case, it went up. The rightmost 0, I followed the end behavior in the right. In this case, it went up. What this will do later is to help me ensure that I've crossed and touched zeros at the right places, and you'll see that when we start getting repeated roots. Anyway, this is the simplest case. Hope this helps. Thank you.